Good morning, everybody. Welcome again for this new colloquium in the Instituto de Astrofísica de Andalucía in Granada, in Spain. And today we will have another colloquium in our Severo Ochoa project.
Sure.
The talk will be given by Dr. Diederik Kruijssen and will be a stellar clustering connection in the formation and evolution of galaxies to the formation and evolution of us. So Dr. Kruijssen will be introduced by Isabel Marquez. Please, Isabel.
Thanks, Rene. Good morning. Do you hear me?
Yes, perfectly.
Okay, good. So first of all, thank you very much for you who are here in real. That's a pleasure for us to have you here. It's a different thing for me. I have always said that 3D changes everything. So thanks a lot. But first, it was the second thing to say. The first one, of course, was to say thank you for our speaker, for Diederik Kruijssen, if I said it right, who is here today with us. Diederik Kruijssen received his PhD from Utrecht University in the Netherlands in 2011, after carrying out his research as an independent PhD fellow at the universities of Utrecht, Leiden, and Cambridge. He then became a postdoctoral research fellow at the Max Planck Institute for Astrophysics, the MPA in Garching. And after 4 years at the MPA, he moved to Heidelberg as a research group leader and Gliese fellow at the Heidelberg University. Currently, he is a staff member in Heidelberg and leader of the Mustang Group, as well as a visiting scientist at the Max Planck Institute for Astronomy, also in Heidelberg, and the Institute of Theory and Computation at Harvard University. He holds an Emazex research group from the German Research Foundation and an ERC starting grant from the European Research Council. Since 2013, he has been awarded, and just listen please, to the Christian Huygens Prize for the Netherlands Royal Academy of Sciences, the Ludwig Biermann Prize of the German Astronomical Society, that's a problem of the pronunciation, but I'll try my best, the Hensberger Prize of Heidelberg University, the Academy Prize of the Heidelberg Academy of Sciences, and the Pastor Schmeitz Prize of the Royal Netherlands Astronomical Society in recognition of his early career achievements. Diederik Kruijssen is a young researcher. You will see, with high impact in fields ranging from star formation over galaxy evolution to the history of the Milky Way and the Galactic Center. He's an excellent lecturer, and in fact, he was tutor of our advanced school of star formation in the Severo Ochoa program. It's a really pleasure and an honor to have here such promising young researcher who is talking about, as René said, stellar clustering, connecting the formation and evolution of galaxies to the formation and evolution of us. And the floor is yours. Thank you very much.
Thank you very kindly for your generous introduction, and in particular also, of course, for having me here. As you said, 3D changes everything, and it certainly does for me. It is absolutely wonderful to be here, and I've already been talking to several of you yesterday when I arrived, but I look forward to continuing those conversations over the next couple of days. So thank you so much for the invitation and for having me. Yes, I would like to talk about how the clustered nature of stars at their formation and thereafter has shaped our origins, from the formation and evolution of galaxies like the Milky Way to the formation and evolution of planetary systems like the solar system. And I would like to start that journey by looking at the universe on the very largest scale. What you see here is the cosmic web. All of those structures here are individual, in this case, dark matter halos from the illustrious TNG project. And when I look at an image like this, I always imagine that every pixel contains countless planets. And if you actually look at it that way, this is an overwhelming abundance of planets. And of course, it's an enormous scale, an enormous dynamic range, right? You wouldn't be able to recognize individual planets here ever. So this is not like something you can easily connect. There's a huge gap in between. And in fact, if you look at the difference in spatial scales, this is spanning 18 orders of magnitude in spatial scale. So what that does is it makes our existence one of the biggest multi-scale astrophysics problems. And I personally think it is the biggest multi-scale astrophysics problem. So you don't actually solve this problem of going from large-scale structure of the universe to eventually habitable planets like Earth. You don't sort of solve that in one go, right? What you do is you cut that up into tractable pieces. So what you can do is you can go from the cosmic web here to individual galaxies. That gives you 4 orders of magnitude in spatial scale. Then you can zoom in further within those galaxies where stars are forming, stellar clusters. It's another 3 orders of magnitude in spatial scale. Now within those clusters, there will be protoplanetary disks in which eventually planets are forming. That's another 4 orders of magnitude in spatial scale. And for somebody who originally comes from sort of galaxy scale astrophysics, I always thought that we're almost there, right? Protoplanetary disks. It turns out to get from a protoplanetary disk to something like Earth, there's another 7 orders of magnitude in spatial scale. So this is huge. But by cutting up this problem into pieces, you can actually start making progress. Now, what I've done here is I've put the stellar cluster here in the middle of this sequence. And that is for 2 reasons. One is it is actually sitting roughly in the middle if you look at the spatial scale range. But also, I think physically speaking, this is the center of this chain. Because towards large scales, stellar clustering drives the baryon cycle within galaxies. The clustering of stars determines where the mass is going within galaxies and how that mass can form stars, how that shapes galactic structure over even larger scales into the circumgalactic and intergalactic medium. But then in turn, if we understand where the oldest clusters come from, we can actually use them to trace galaxy formation and assembly. It's going the other way back. Towards smaller scales, because planets form in those protoplanetary disks, that are orbiting stars in these clustered environments where stars are forming, the clustered nature of those stars can perturb and destroy protoplanetary disks and therefore influence the planet formation process. And then finally, I'll show that the stellar clustering can actually modify over long timescales the properties of the planet population. So in the end, it's actually stellar clustering that is really the key link within this entire network of physics. So I'll start here with the first point, of how stellar clustering drives the baryon cycle within galaxies. And the key point here is that star formation within galaxies is a clustered process, right? If you see a star forming, it is likely that you see another star forming kind of next to it. And you can actually see that effect in numerical simulations. So what I'm showing here is work by Ben Keller in Heidelberg. What you see here is 4 different simulations of a Milky Way-like galaxy. And they are using exactly the same initial conditions, the same subgrid physics, as we call it. The only thing that differs between those models is the feedback model. What that is the way in which the young stars, and in this case, the supernovae, distribute their energy and momentum back into the interstellar medium. And the difference here is simply only the delay time. So you form new stars, how long do you wait until you let the supernovae go off? It ranges from 0 megayears, so then they go off immediately, to here in the end 30 megayears. And what you see is that there are actually qualitative differences in what this galaxy looks like. We only change that one parameter. Now it turns out that the reason for this is actually that my pointer just... You only see gas here? Yeah, you only see gas here. And for one reason or another, my pointer doesn't want to continue. So I'm just going to do it like this. There. So it turns out there is a reason for this, and that is as a function of this delay time, this is now the 2-point correlation function between young stars. You see that as you increase the delay time, the 2-point correlation function becomes steeper. What that means is the stars are more clustered. And that is because if you wait longer with the feedback, the gas can collapse further, and the star formation will be more centrally concentrated. All the supernova explosions go off in the same place. And that is then eventually driving these gigantic bubbles in the bottom right figure. So, of course, this is only showing the example of supernovae. The problem is, of course, is that feedback is extremely complex because it's not just supernovae. Feedback connects stellar winds, supernovae, of course, photoionization, radiation pressure, and so on. And the interplay between those mechanisms is extremely complex. And also the interplay between these mechanisms and the surrounding medium is extremely complex. So the way we've been trying to address this is basically by using observations to constrain how much energy and momentum is effectively put into the surrounding medium by the combination of all of those feedback mechanisms, by measuring the timescales for molecular cloud destruction in galaxies. If you can figure out how quickly the clouds in galaxies are being destroyed, then that tells you something about how quickly the energy and momentum is being put into the surrounding medium. And then you can use that to model feedback in simulations and get the stellar clustering right. So this is basically as a sneak preview for Melanie's colloquium tomorrow. Melanie will be talking about the baryon cycle at length, but I'd briefly like to highlight one result, which I believe you're not actually going to show this plot tomorrow, are you? No, okay, good. So I'd like to highlight one key result that is important for what I'm presenting here. So basically, in short, we've developed a method that allows us to basically directly measure these evolutionary timelines of molecular cloud evolution, so how long molecular clouds live in individual galaxies that you see here. And we find that these molecular clouds live for about 10 to 30 million years, about one dynamical time. But then most importantly, for what I'm trying to, what I'd like to show here, is that the clouds are dispersed by massive stars. So the massive stars appear here at the beginning of the purple part in the middle, and the gas is gone at the end of the purple part. So the massive stars disperse the surrounding clouds in about 1 to 5 million years. That's very quick. It's actually quicker than you typically expect supernovae to go off. So what this means is that these so-called early feedback mechanisms from photoionization and stellar winds are really important in driving cloud destruction. Now, what you can then do is you can measure now that time scale. And because of that, you can measure the star formation efficiency, you can measure the molecular cloud radius, and you combine all of those quantities in a simple expression here that tells you what this is what we call the specific terminal momentum. So it is the momentum put in by the massive stars per unit stellar mass. That's why it's called specific. And terminal is because this is at the end of cloud destruction. So this is the total momentum that you have needed to put in order to destroy your cloud on that timescale T feedback here, which we can now measure. So all of those quantities are now observables. This here is a constant of order unity, so this is actually not important. And that means we can actually just measure this number. So we know exactly how much momentum a young stellar population, as a function of its mass, puts into the surrounding medium. And if we assume that this feedback front is expanding according to a self-similar solution, you can actually differentiate it and you can solve the injected momentum as a function of time. It's just a parallel function of time here. And you know, in your simulation, at every moment in time, how much momentum a star particle is putting into the surrounding medium at that moment. And this is taken directly from observations. So you can take those timelines that I just showed on the previous slide, and you can ask, okay, what does that specific terminal momentum actually look like across these 10 nearby galaxies? Here shown as a function of galactocentric radius. And what you see is that this number is remarkably constant. This is only a factor of 2 variation across the local galaxy population. So that means is we can basically, to first order, I'm sure there are physical variations of this number, but to first order, you can just take this number and plug it into your galaxy simulation and say, okay, well, that is how the universe injects feedback into galaxies. Here I'm now showing the same number, the same specific terminal momentum as a function of this cloud destruction timescale, the feedback timescale. And now the lines are overplotting the expectations for different individual feedback mechanisms. So here, this is for radiation pressure, what you would expect. This is for a fully radiative stellar wind. And what you see here is that the data do not follow any of the individual expectations. So that leads to a philosophical question. Should I follow the data or my instincts? And I personally believe that the observations are always right and my instincts are always wrong. So I should follow the data. And I will go a step further, and I would say that this empirical specific terminal momentum is the only way of solving this complex nonlinear interplay between the different feedback mechanisms and the surrounding medium. what their impact is on the surrounding medium. This is the only way, and that's why it's so important to get those observational measurements. So with that, we've now developed a new suite of cosmological zoom-in simulations that uses this new feedback model that is exactly coming from the observations. In addition, we have explicit ISM cooling. We track the chemical abundances of 36 elements and their isotopes for a total of over 100. We have a new star formation model, and we have a subgrid model for star cluster formation and disruption, where we actually can follow the properties and demographics of the entire star cluster population, which will be important in the next part of the talk. And all of that we're solving on a moving mesh using the Arepo hydrodynamics code. And as you might imagine, there's a lot of ingredients. It's really teamwork here that I'm about to show. Yeah, so what does it look like? It looks like this. So this is not yet a cosmological zoom. This is an isolated Milky Way-like disk galaxy in which the feedback that is driving the bubbles here, right? You see here a bubble expanding, for instance, or whenever stars form, here's a bubble. All of that feedback that you see is coming straight from the observations. So this is how the universe does it, right? We cheated. We decided to not try and solve it from first principles. We just put in the right solution. Now we can, of course, because it's a simulation, we can ask the question, how does this empirical feedback change the properties of the galaxy? And this is the answer. So here on the left, you see what a galaxy looks like in an experiment where we only use supernova feedback. And here is a galaxy where we added this early empirical feedback. And you see that, again, the qualitative structure of the galaxy is different. On the left-hand side, the bubbles are much bigger. There seems to be a lot more substructure, whereas on the right, it's a lot smoother. In a way, that's weird, right? We add more feedback and the galaxy becomes smoother. That's weird. It turns out that has a real impact, and this is actually the reason why that difference exists, has a real impact on where the supernovae go off. So here, the blue line is if we only have supernovae, and we see that the ambient gas density where the first supernova goes off in clouds is higher if you don't include this empirical feedback than when you do include the empirical feedback. And the reason is the empirical feedback starts immediately. So it starts clearing the gas around young stars and sort of creates nearly a vacuum bubble around those young stars. And then the supernovae go off. So instead of the supernova energy being cooled and radiated away immediately, now the supernova energy is being deposited in a hot bubble already. And that way it can have a much greater impact than actually coming out of the disk, and I'll show that in a moment. But most importantly, the initial structure of the cloud is now determined entirely by the early feedback. So if you only have supernova feedback, your cloud will keep collapsing and form stars, and the stars will be extremely clustered. Or if you add this empirical feedback, it will stop the collapse of the cloud much earlier, and you'll get more dispersed star formation. And that leads to this overall difference in disk structure, where here, the stellar clustering, and therefore the feedback, is very concentrated, and here it is a lot more dispersed. And you can actually see that in the stellar image. So this is now showing the stars in these galaxies, and you see on the left-hand side that the degree of clustering is much greater than on the right. And you see exactly the same here, again, in the two-point correlation function. So by adding this early feedback, we've basically made the galaxy smoother on the cloud scale, and that translates into the galaxy being smoother at large. And it turns out that is not just the internal structure, it actually changes the total baryon cycle within the galaxy. So this is now the outflow mass loading. What that is it's the outflow, the mass outflow rate from the galaxy in units of the star formation rate. And what you see is that if you only have supernovae, your outflow rate is the mass loading is about unity. Your outflow rate is about the same as your star formation rate. But if you now add the early feedback, it's about 1/10. So that means that instead of, and the star formation rate is the same, by the way, in both cases. So it means that instead of blowing the gas out of the galaxy and regulating your star formation that way, what this early feedback does is it just puts the gas in a non-star forming state. It heats the gas, it pushes away the gas a little bit, but doesn't blow it out of the disk. The gas is just hanging around in a different state, like atomic gas. It is not generally star forming. So this is actually a nice prediction for future observations with the SKA, where we will be able to say, okay, well, galaxies should have a larger atomic gas budget if you use that model than if you use the supernova only model. That's a very direct prediction that we should basically be testing across the galaxy population. Okay, so what this does is it gives us a way of modeling the feedback in galaxies and getting the stellar clustering right. So with that, I've basically shown how stellar clustering drives the baryon cycle in galaxies. Now we can go the next way. With that in place, we can say, okay, now that we have the stellar clustering, we can actually start using those clusters to trace galaxy formation and assembly. And what I'd like to use for that are globular clusters, of which you see an example here. So for those of you who are not too familiar with globular clusters, basically every reasonably massive galaxy has globular clusters. They're very old, order 10 gigayears. They're massive, about 10 to the 5 solar masses. And they're typically also quite compact with radii of a few parsecs. And the key questions that people typically ask when they're interested in globular clusters is, how did they form? And what do they tell us about the formation and assembly history of the Milky Way? Because they're so old that they probably have some imprint of the early birth epoch of our galaxy. Now, to answer these questions, we developed the next suite of simulations called the Emazex project. So what you see here is a large cosmological volume, and then within that, we simulate the individual galaxies using a subgrid model for star cluster formation and evolution. Basically describes the formation and evolution of the entire star cluster population as the galaxies are forming and evolving. And schematically, what that looks like is we use in this project, we use the galaxy formation model from Eagle, where we have the hydrodynamics, the overall stellar and galactic dynamics, and we have stellar evolution, so metal enrichment and stellar evolutionary mass loss. And we couple that to the Emazex model for star cluster formation and evolution that tells us, as a function of the local conditions in the interstellar medium, what fraction of the stars are actually born in clusters? What is the initial mass spectrum of those clusters? So that's the formation side. But then in addition, it tells us, based on the local tidal field, how much mass those stellar clusters are losing at every moment in time and how quickly they are dissolving under the influence of external perturbations and the tidal field, and also, of course, stellar evolutionary mass loss. So putting that together, and this is the movie I showed on the first slide, what you see here is a cosmological zoom-in simulation of a Milky Way mass galaxy. And in gray, it's showing the gas. And in the colors, in the dots here, you will see stellar clusters forming. And they're color-coded by their metallicities, where blue is very metal poor. So you now see the first blue ones forming early in the universe when everything is still relatively unenriched in metals. And then as the galaxy is collapsing, you'll start to see sort of brighter yellowish, orangish colors. And these are more metal-rich clusters. What you will also see at some point is around here is another galaxy will come in and merge with the central galaxy. And that other galaxy will be bringing in its own stellar cluster population. There it is. And notice that these clusters are bluer. These are more metal poor. It's because this is a lower mass galaxy that was less good at enriching its clusters and enriching its mass. So these clusters are then being contributed to this central galaxy. That already tells you something. Hey, there are actually differences in the properties of those clusters depending on where they came from. And we will use that. So putting this together in Emazex, we've run 25 cosmological zoom-in simulations of Milky Way mass galaxies and their satellites, hundreds of simulations to really figure out, okay, which elements of the model are important in determining what the predictions exactly are, to really basically make ourselves confident that we can, which results we can trust and which ones we cannot. And then finally, we now have a 34 megaparsec periodic volume that contains of the order 80 Milky Ways and even a Fornax galaxy cluster type thing that you see forming up here. So with Emazex, we've had two main results. One is we demonstrated using Emazex that globular clusters are basically the natural outcome of high redshift star formation. So the extreme conditions that you see in high redshift galaxies of intense star formation naturally leads to globular cluster populations that we see today, more than 10 gigayears later. But the part that I would like to focus on here is the second result, is that we can actually use globular clusters to reconstruct galaxy formation and assembly. We can kind of use them like fossils to figure out how galaxies form. And to do that, I will focus here mostly on the age metallicity distribution of globular clusters. So what you see here is the observed age metallicity distribution of globular clusters in the Milky Way, here age on the x-axis and metallicity on the y-axis. What you see here is this sort of bifurcation into two branches. Actually, this is cut here at a metallicity of -0.5. If you continue, then this branch here that looks vertical will actually bend over a little bit and go that way. So it will be above the other branch. So what that means is at a given age, we've got a branch that is more metal poor than the other one. And the classical interpretation here is that the branch that you see going straight up here on the right and that will then bend over, that is composed of in situ globular clusters that formed within the Milky Way itself. Notice, by the way, that it does go down quite far, right? So metal poor clusters can also be in situ. The Milky Way was a small galaxy once, long ago. But then these is the idea on this sort of inclined branch towards the left, formed in satellite galaxies that were later accreted onto the Milky Way because those satellite galaxies had a lower mass and therefore a lower metallicity. Now in Emazex, we can actually test this directly. So what you see here are 6 different Milky Way mass galaxies with their age metallicity distributions, where the dots are the globular clusters and the contours are basically the field star formation and assembly and enrichment histories. So what you see is the first order, whenever there is intense star formation, so the contours get close together and there is a burst of star formation, you also get globular clusters. So to first order, globular clusters just trace the star formation or the intense star formation history of the host galaxy. And by and large, you see that all of those distributions do the same thing as they start metal poor and they end up metal rich, right? So they go from the bottom right corner to the top left corner. But there are real differences between those plots, right? So here the middle left looks like it's quite gradual, whereas the bottom right is super steep. It turns out that these differences actually correspond to differences in assembly history. So I'm now showing merger trees of those galaxies here on the left, where the middle left panel here you see has a very sparse merger tree. Very few accretion events, grew slowly, and that's why it's so shallow. Whereas the one here on the bottom right is a very rich merger tree, a very violent history basically, and that is why it accreted or it enriched and formed clusters so quickly and shot right up at the beginning. The other thing we can do here is we can figure out, okay, I see some low metallicity, younger globular clusters here. Well, it turns out they're color-coded by galactocentric radius here. These are sitting far out, and it turns out in the simulation, we can actually see these came from accreted galaxies. So this idea that a satellite branch here is what you typically call it, is basically tracing globular clusters that came from accreted galaxies. That's correct. And what that allows us to do is link individual globular clusters to their progenitor galaxies. And that is something we can start doing for the Milky Way now. Now with Gaia, of course, everything changes because next to ages and metallicities, you also have extremely well-constrained orbits. So I'm showing that here now in energy angular momentum space, and here 2 other angular momentum components. And what you can do in this kinematic space is you can do clustering to figure out which globular clusters came from the same progenitor galaxies based on their orbits, right? So let's say you've got a satellite galaxy with its own globular clusters and that's being accreted, it's being tidally shredded in the potential of the Milky Way. And then those clusters that are coming from that dwarf galaxy will have similar orbits. And you can pick that out in this type of diagram. So this is work by Masari and collaborators, and what they've done is they've basically assigned individual globular clusters to different progenitor galaxies here. Basically saying those clusters likely came from the same galaxy. And what we can then do is we can use those groupings to go to Emazex and ask, okay, what were the properties for groups like that, for groups of globular clusters like that? What were the properties of the progenitor galaxies? Now, that is a little bit of a hard to solve problem directly, say analytically. So to solve that, what we did is we used machine learning techniques. We trained an artificial neural network on the Emazex simulations to say, okay, we look at all globular clusters that came from one galaxy, and we look at their ages, their metallicities, their apocenter distances of their orbits and their orbital eccentricities, to then train the network on the Emazex simulations to predict what was the mass of the satellite galaxy that these clusters came from, and at what redshift did that satellite merge into the central galaxy. So we trained that on all globular cluster rich accretion events across all Milky Way mass galaxies in Emazex. So that way be able to make that link directly. And then we applied that to those groupings of globular clusters in the Milky Way that likely came from the same progenitor. And these are the results. And so what you see here now is the mass of the progenitor galaxy, the stellar mass, and these are the posterior probability distribution functions for each of the 5 groups of globular clusters that were identified by Massari and collaborators. You see different histograms in each panel. That is because for some clusters, it's not exactly clear which galaxy they came from. Some clusters are ambiguous. So we basically tried all possible permutations to see if the membership assignment of individual globular clusters mattered. And as you see, by and large, it doesn't matter that much, right? So the broad classification of the globular cluster seems to be right. Now, what we see then here is that there was a range of different masses, but there were basically three massive events. So Kruijssen, Gaia Enceladus, which you might have heard of in press releases and so on, and the Sagittarius dwarf galaxy were all quite massive, with masses between 2 and 3 times 10 to the 8 solar masses. And there were 2 lower mass galaxies just under 10 to the 8 solar masses, the progenitor of the Helmi streams and Sequoia. Now, those 3 galaxies here had relatively similar masses, but they accreted at vastly different redshifts. And you can tell this because the Kruijssen globular clusters have much smaller galactocentric radii, for instance, than the Sagittarius globular clusters, which are much further out. And that tells you they accreted onto the Milky Way when the Milky Way itself had different masses. So if we now look at the distributions of the accretion redshifts, we see that Kruijssen was the first one to accrete. Gaia Enceladus followed later, about 9 to 10 gigayears ago. 9 gigayears ago. And then Sagittarius, of course, is very recent. We still see the debris of Sagittarius orbiting the Milky Way, actually. Now, because the Milky Way had different masses at those different times, we can calculate the merger mass ratio. And it turns out that Kruijssen is the most major merger the Milky Way ever experienced, because it accreted the earliest, when the Milky Way was still relatively low mass. Now, I say most major, it's actually still absolutely tiny. The stellar mass ratio here is 1 to 30. What that means is the Milky Way never experienced a major merger. And maybe that's why we exist. So what you can now do is you can put all of this together and start building the merger tree of the Milky Way. And that is roughly what it looks like. So we've got those 5 accretion events that we connect here to specific moments in time that accreted here on the main branch that you see in the middle. That's the stellar mass growth of the Milky Way. Based on the global statistics of the galactic globular cluster system, we expect another 10 mergers to have happened. It's just we've not been able to identify those yet. Some of them might not have had globular clusters. Some of them might have been too low mass, so then we wouldn't be able to find them that way. But we do expect them based on the total demographics. Right, so you see here Kruijssen merging first, and the progenitor of the Helmi streams, Sequoia, Gaia Enceladus, and eventually Sagittarius here very recently. Now, to me, this is super exciting because I've always thought about merger trees as something that simulators draw. When they have a galaxy simulation, you can build a merger tree. But now we've actually started to do this for the Milky Way. And this is just the beginning, because people will be finding all of those other mergers. And with Gaia, there's actually already been huge progress on this. So this is from 2020. It's already outdated. And that's how exciting this field is. It's just moving forward at this crazy pace. Another thing that we were very happy with is that Kruijssen was originally a prediction of Emazex. And it's now been found with Gaia and other surveys. They've actually found the debris. And based on the globular cluster population, we said there had to be this merger. We found the globular clusters. And now the stars have been found too. So I think that is a great, that gives us confidence, right? That these models can actually be used to make sensible predictions. Okay, so where do we go from here, right? With Emazex, we've been modeling this galaxy population and their globular clusters across this entire 34 megaparsec volume, where you've got this very large galaxy population. And what you can do with that is you can actually start trying to reconstruct the assembly histories of galaxies other than the Milky Way. So this is work by Sebastián Trujillo Gómez, who has basically looked at the complete galaxy population across this 34 megaparsec volume and looked, okay, as a function of the metallicity, the projected radius, the projected angular momentum and so on of clusters that you would see in other galaxies, can I tell if they are in situ or accreted? And by training, again, a machine learning model on these data, he's actually to predict with high confidence of individual clusters in other galaxies, if they were accreted or formed within in situ within the host galaxy. And that's the first step to being able to do this type of science for other galaxies too, where we will be able to look at other galaxies and say, this is the merger tree, more or less, of that galaxy, and start to compare the current galaxy properties as a function of what their assembly history was. So that is where we're going on that front. Then another really nice project is that you can look at the cosmic distribution of globular clusters. So this is something Euclid will measure. So this is the cosmic two-point correlation function of the dark matter, the gas, the stars, and the globular clusters. This is work by Louise Kluge. This is the merger tree. Sorry? Somebody said something on Zoom, but I think that was by accident. Okay. So this is work by a bachelor's student, or was a bachelor's thesis by Louise Kluge in Heidelberg. And what you see here is that basically within size scales of about 20 kiloparsecs, globular clusters are less clustered than the stars. Outside of that, there is a little bit of an excess, but to first order, globular clusters really just follow the stars, right? And here on larger scales of above a megaparsec is the two halo term that kicks in, and they follow each other just exactly. Now then finally, with James Webb, we can now actually start predicting what the population of proto-globular clusters at high redshift look like. And this is really important because there were multiple ways of getting from A to B, right? There were multiple ways of saying, well, you know, there was some degeneracy in models. This is how we can reproduce the present day globular cluster population. If you want to actually test your model well and falsify it and learn, you need to predict also how they started. And with James Webb, we can now do that for the first time. We can predict here, for instance, what the UV luminosity function was of young proto-globular clusters as a function of redshift. And James Webb is actually going to measure this. So I think with these types of observations, we're approaching the point that we are actually obtaining a reasonably sensible and complete understanding of where globular clusters came from and how you can use these to reconstruct galaxy assembly. Okay. So we've gone from using or understanding how stellar clustering drives the baryon cycle within galaxies to then using that stellar clustering to figure out how galaxies formed, including the Milky Way. I'd now like to zoom in and go within the clustering of star-forming regions and show how they perturb and destroy protoplanetary disks. And that is important because, as I mentioned, star formation is hierarchically structured. So you get those hierarchies where stars tend to form close to one another. And in those substructures that you see here, external photoevaporation of protoplanetary disks, and in the bound regions also dynamical interactions between stars, are very common processes. You actually see some of the stars being thrown out here. This is by dynamical interactions. But the thing that is actually the most common here is external photoevaporation. What you see here is Orion. And the idea that external photoevaporation matters to protoplanetary disks has been known for nearly 30 years, right? These are the so-called proplids. They're those beautifully shaped protoplanetary disks in this region that here are just shaped by the nearby massive stars, and you can actually see the orientation kind of matching as well. So we know that the fact that stars are clustered at birth affects the properties of the protoplanetary disks and affect the lifetimes of the protoplanetary disks. You can actually, I mean, this is just an image, but here you can actually see it quantitatively. So this is here as a function of the separation from one of the massive stars in Orion, showing the dust mass of those protoplanetary disks. You see that massive disks are basically missing close to this massive star. And that's because they've been photoevaporated externally. So you can try and model processes like this. So this is now showing an n-body simulation of stars in a cluster where each star has its own protoplanetary disk. And because of the dynamical interactions between the stars here, what you see is that, okay, that was somebody unmuting. What you see is that the protoplanetary disks are being destroyed by those dynamical interactions. You see their material being thrown around within the cluster. So these types of processes you need to model. The photoevaporation and the dynamical encounters you need to describe in order to be able to predict how long your protoplanetary disks live as a function of environment, and thereby what planets might eventually form there. Now, the way you can do this is by basically starting from first principles of how the interstellar medium is structured within a galaxy. Right? You need to know how clustered the stars are. And it turns out the clustered nature of star formation depends on the local gas density, because that seeds where your stars are forming. Now, there is a huge literature that shows that the gas density probability distribution function is a log normal, and that the width of that log normal distribution increases with the gas pressure. So in higher pressure environments, you'll have larger density extremes, basically, in your gas. So what you can do is you can take the gas here and you can say, okay, at low densities here, we'll have long free fall times of the gas. It will take very long to collapse. And here at high densities, we'll have very short free fall times. Now, because of that, here on the left, you will achieve a low star formation efficiency. A small fraction of the gas will be converted into stars because it takes a very long time for the gas to collapse. Whereas on the right, it collapses very quickly. So you manage to go through many free fall times and convert a large fraction of your gas into stars. Because of that, here on the left, you form those sort of sparse associations, like the one you see here. Whereas on the right, you form compact, dense stellar clusters. Now, because the width of this PDF is set by the gas pressure, you can define a relatively simple hydrostatic equilibrium disk model and define this PDF entirely by galaxy scale quantities. You can define it as a function of the galactic gas surface density, the angular velocity, so how quickly the disk rotates, and the tumor Q parameter. If you combine those three numbers, you can define this entire gas density PDF. And therefore, you get the stellar density, which you can then use to predict the initial cluster mass distribution, the stellar initial mass function, how you sample from that, the local far UV radiation field, and therefore the external disk photoevaporation rate, and because you have the stellar density, also the dynamical destruction rate by stellar flybys. And if you have these things, you can predict exactly how long your disks are going to live as a function of this large-scale galactic environment. And that is an exercise that we did now 2 years ago. And this is basically the result. So what you see here is distribution of stars predicted. Here is a two-dimensional histogram in gray as a function of the stellar number density and the local far UV flux density, so how irradiated the protoplanetary disks are. And here the left-hand panel we'll focus on first is the solar neighborhood. The right-hand panel is for conditions typical in the central molecular zone, so the center of our galaxy. So what we see here is this large sequence basically of where we expect protoplanetary disks or stars to be forming. And what is overplotted here are those bands are actually observations of nearby star forming regions. So you see that nearby star forming regions actually match this distribution that we predict based on the local conditions quite well. What you then see here in blue are predicted isochrones of how long your protoplanetary disks live. So this horizontal part is set by external photoevaporation. So if your flux density is around here, your protoplanetary disk will be gone in about a megayear. Down here, it will be about 3 megayears. Whereas the vertical part on the right is set by stellar dynamical encounters. So if you're a protoplanetary disk down here, you will live briefly because there will be some dynamical encounter that will destroy you. Now, what is the key thing here is in the solar neighborhood, there's only a few % of the disks is disrupted in less than a megayear. So basically, the solar neighborhood is not a disruptive environment. However, in the central molecular zone, so the central 500 parsecs of the Milky Way, more than 90% of the disks are disrupted in less than a megayear. And that is really important. You might think, well, what do we care about the galactic center, right? I know Reiner cares about the galactic center. I care about the galactic center. But why would we care about how protoplanetary disks are being destroyed in the galactic center? We live here. Well, it turns out that across cosmic history, most stars formed under conditions that we see in the CMZ today. And that's because the peak of the cosmic star formation history was at redshift 2. Most stars formed, I think the median star formation and the median age of stars in the Milky Way is something like redshift 1. Most stars did not form in the solar neighborhood, not in those conditions. Stars formed under these types of conditions. So if we look at the planet population that we see today, they will have been subjected to these types of conditions. And their protoplanetary disks will have been subjected to these types of destructive conditions. That's why it's so important. And if you then look at what you expect the disk lifetime distribution to be, you see that you expect disks in the CMZ to live 5 times shorter than in the solar neighborhood. It's about half a megayear is the median here, whereas in the solar neighborhood, it's about 3 megayears. And that's a quantitative prediction here, right? You can test that with James Webb, with ALMA, and also with IRAM if you start looking at the chemistry of those disks. So I think this is really important going forward. It's just a prediction at the moment. But I think it's a really existential prediction and we should try and test it. So with that, I think I've shown that the expectation is that stellar clustering actually does really perturb and destroy protoplanetary disks. What now, of course, the key question is does stellar clustering actually modify the properties of the planet population? How do you go about that? How do you determine if the external environment affects planet populations? Because that's difficult, right? Most known planets have ages older than a gigayear. So that means that whatever overdensity of stars existed when those systems were born has long been erased. Typically, these regions disperse over much shorter timescales. But it might be possible to detect stellar clustering in position velocity space, in 6-dimensional phase space, basically by finding co-moving groups. And it turns out that is now something you can do with Gaia. So to test this idea, what we did is we took all known exoplanet host stars, for which we had radial velocities and total complete 6D phase space information. We determined the 6D phase space density around these stars. And then we checked for biases to see, okay, depending on what the local phase space density was, were there fundamental intrinsic differences in the planet population properties? And then compare those planet properties as a function of this ambient phase space density. And we kept checking for biases all along. That's really important because, yeah, it matters what observatory you use if you look at planets, et cetera, et cetera. So this is really critical. Okay, so what does that look like? Here I'm showing two examples, here just in galactic coordinates, X and Y, of here the star in both cases is a planetary system. And then these are nearby stars, all the other symbols. So what you see here is that there is no phase space structure here in physical space, right? So here HD something and WASP-12 both look similar, and they both are sitting in the middle of a scatter plot of field stars, right? That's what the Milky Way looks like. However, if we look at kinematic space, the situation is very different. What you see here is clustering in kinematic space, very clearly. So this is azimuthal velocity and radial velocity within the Milky Way. But then now HD something is not sitting in this overdensity that you see here, whereas WASP-12 is sitting right in the middle. And it turns out if you then plot actually a histogram of what the phase space density distribution in the environment of those planetary systems look like, it's almost always a double log normal, or something you can at least fit reasonably well by a double log normal. And then what we do is we use Gaussian mixture modeling to basically describe this and calculate the probability that here the vertical line is the planetary system, calculate the probability that it belongs to this right-hand side component. The right-hand side component we then refer to as an overdensity, and you see here WASP-12 is indeed sitting in an overdensity with a probability of 95%, whereas HD something here is very, very clearly sitting in the field. Probability that it's part of this high density component is about 10 to the minus 4. So what we got here is field systems, field exoplanetary systems, and overdensity exoplanetary systems. Now note, by the way, I'm being a little bit liberal here with how I'm using the term overdensity. We do not know if the phase space density here reflects the birth cluster or something else, right? This is just the clustering we see today in phase space. Now then, as I mentioned, you need to check for biases. So that's what we do here. So this is showing cumulative distributions of the stellar mass, the host mass, stellar metallicity, the stellar age, and the distance from the sun. We make stellar mass and age cuts to make sure we're looking at least relatively similar stellar systems. And then showing this in blue for the field population and in red for the overdensity population. So what we see is if we do a KS test between those is that the stellar mass, metallicity, and age are indistinguishable statistically. They're the same between both samples. So any differences we see in planet population properties between field and overdensity systems cannot come from differences in host stellar properties. We do see that host stars in the field are closer to Earth than those in phase space overdensities. There's nothing we can do about that. That is just how the solar neighborhood is structured. But it turns out if we make a cut here at about a distance of 300 parsecs, the distributions are identical. And the results I'm about to show do not change when we make that cut. So that means that the results are not coming from a distance bias. Okay, so what do things look like? They look like this. This is the distribution of known exoplanets in the field on the left and overdensities on the right, as a function of their semi-major axis within the planetary system and the planet mass. This is a radical difference. And you can quantify that. So it turns out the median semi-major axis differs by an order of magnitude. It turns out that 92% of all known hot Jupiters, so these are massive gas giants that are sitting at small semi-major axes, 92% of all known hot Jupiters are sitting in overdensities. In fact, the few hot Jupiters that are in the field or in field systems are actually in binaries. So if what the suggestion is here is that if hot Jupiters are being produced by some sort of perturbation that you get in overdensities but not in the field, And here, these are probably produced because they're sitting in binaries, and the binary is perturbing the planetary systems. So when we saw this, we were shocked, really. And we tried for a long, long time to get rid of the results because we thought we made a mistake. But it turns out it's not just restricted to this observable. So there is a well-known problem, so to say, within exoplanetary sciences, which is called the Kepler dichotomy, which is that there is an excess of single planet systems. So there are more single planet systems than you might expect based on a theoretical multiplicity distribution. So here's showing the number of planets per system. Predicted here is the little stars. And then it turns out the observed distribution here is in black. So we got a huge excess. And it turns out that excess is mostly coming from the overdensities. So planetary systems in overdensities tend to have only one planet, or at least more often than those that are sitting in the field. Again, being suggestive that perturbations somehow maybe ionize the planetary systems, kick out planets, and in the end, you're only left with one. So that's interesting, is we actually see this very clear difference between overdensities in the field. But it turns out it's not only the architectures of the planetary systems that are being affected by this. Another key Kepler result is the so-called radius valley, which you can see here. So this is the orbital period on the x-axis of the planets, and here the planet radius from 1 Earth radius to 4 Earth radii. And you see that there's this depression here in the planet density, which is called the radius valley. There are fewer planets with a radius of about 1.8 Earth radii. And this is normally explained by the idea that planets above this have, like these are called sub-Neptunes, have a hydrogen-helium gas envelope. But if they lose that, they move under this radius valley and they are basically only left with this rocky core. So the idea is that these are rocky planets below the line, and above the line they're sub-Neptunes. So you've got sub-Neptunes and super-Earths. Now what we can do now is we can try and separate this by field and overdensity system. And it turns out that we find no rocky planets, so no super-Earths in the field. We only find those in overdensities. And it's a small sample, but it turns out the result is statistically significant. If you run a KS test or if you use other statistical metrics, it turns out the probability of getting this is only a few times 10 to the minus 3. So of course we need more data, but this is at this moment is already very suggestive, is that apparently the stellar clustering and the perturbations of the planetary systems that you get is somehow capable of determining, okay, which of my sub-Neptunes are actually going to be losing their atmospheres. And we have some ideas of what the physics might be that are driving this. But of course, that's not yet an answered question. Okay, so as I said, we've been trying to get rid of this result for a long time because we thought this was some conspiracy in the data. We thought it had to be fake. So we tried for more than a year to get rid of the result. And we tried doing that by varying the threshold probabilities for classifying what is a field system, what's an overdensity system. We changed the cuts in the stellar age, metallicity, distance, so on. We restricted ourselves to only single exoplanet detection methods. We restricted ourselves to only using single exoplanet observatories, like only using Kepler. But nothing got rid of the result. So if you have an idea of something that we missed, please tell me, because I would like to know. But at this point, what the suggestion is that stellar clustering shapes planetary systems. And in the context of this talk, that's pretty cool. But you know, before we party hard, I think we're not there yet, because there is one elephant in the room, and the elephant in the room is, what are those overdensities? What are they? Now in Gaia, we can just look for it. And it turns out, so here's showing now, as a function of galactocentric radius, showing here the azimuthal velocity, so just rotation in the Milky Way, showing a filtered or median subtracted version of basically what the structure is of stars around the solar radius. Here in colored dots, you see the exoplanets overplotted. And what you see is that the overdensities that we see in phase space, so the red is basically all the overdensity systems, that correlates with the structures that you see here in gray for the entire galactic disk that are spanning multiple kiloparsecs. These are very well-known features. These features are thought to be produced by perturbations from satellite galaxy passages, spiral arms, and the galactic bar. These are galactic dynamical features. They are not remnants of stellar clustering at birth. So one way or another, these galactic dynamical features over many kiloparsecs can have an impact on planetary systems. At least that is the suggestion. Reiner.
Are they long-term stable, these perturbations?
Ah, good question. Are these perturbations long-term stable? They can live for several gigayears. However, the stars that are sitting in them can move in and out of them. And that is, of course, is a problem here, right? Because why would the current position of a planetary system in an overdensity or not determine what happened to the planetary system? I personally think the only solution to that is that there must be a population of stars in the Milky Way that tends to spend time in those overdensities rather often. And actually, if we look at the overall demographics of the planets we looked at, the planetary systems that we looked at, the vast majority of them are actually sitting in overdensities, right? So it suggests that is a common state, and probably also that those systems actually spend a lot of their time in those overdensities.
What's the ratio of stars in overdensities to stars in the field?
So that is, no, it's 4 to 1 or so. But yes, more stars in overdensity. Yeah, but what the issue is with that, I mean, this is not completeness corrected or selection function corrected, whatever, right? So you cannot use it as an absolute number. But for what we have, that statement is true. So then what you can do is you can say, okay, what do the stellar populations within single overdensities look like? Now, it turns out here, we look at the host stellar age here. It turns out that independently of whether these are hot Jupiter hosts or cold Jupiter hosts, they have a very broad age distribution. So again, these are not coming from birth clusters or whatever, right? Clusters do not form over gigayear timescales. So again, this is heterogeneous. If we look at the magnesium over iron versus metallicity distribution, right? This here is the thick disk, this here is the thin disk. We see that the distinction between field and overdensity does not correspond to thin disk versus thick disk. They're basically all thin disk. That one here is thick disk, and I'm sure that, yeah, if there were any thick disk stars in the sample, they would probably classify as field, not as overdensity. Fine, but that is not the main distinction. The other interesting result is if you actually look at this, if you look at the hot Jupiter to cold Jupiter ratio, and here showing that for the field, the planet demographics differ between different overdensities. That is also nice because there's different overdensities, different features that I just showed here. So, you know, here, this one is called Sirius, this one is called the Hyades, that one is called the Hercules overdensity. If you look at those different ones, they've got different hot Jupiter to cold Jupiter ratios. There's another one called the ZVZ spiral, the phase space spiral, is excited by the passage of the Sagittarius dwarf galaxy that I showed before. That one has the highest hot Jupiter to cold Jupiter ratio known, and it's a factor 10 higher than in the field. This is exciting because those different overdensities have different evolutionary histories. So that might be a way of actually teaching us how those overdensities are actually impacting the planetary systems. So the conclusion so far is that galaxy evolution is somehow capable of affecting planetary system architectures over long timescales, well after planet formation has completed. And this is a completely new dimension in terms of understanding exoplanets. This dimension has not been considered in planet formation models, planet evolution models whatsoever. But I think going forward, right, if we're interested in what shapes the planet population, we need to account for this. And I think with upcoming facilities, we're really going there. So what we need is two things. We need statistical samples, large statistical samples. So with Ariel getting atmospheric properties, for instance, of 1,000 planets, brilliant, we need that. We also need extreme objects, things that defy our understanding and knowledge, because that will tell us also where the processes might be acting. And we not just need that of planetary system architectures, but also things like atmospheric chemistry, because, you know, if the presence of an atmosphere can be impacted by stellar clustering, as we saw with the Radius Valley earlier, then surely atmospheric chemistry might be affected as well. And we need to investigate it. We have no idea. So what we need is precise orbital dynamics. We need to trace perturbations and migration of planets within the system, but also of the systems themselves within the Milky Way, and eventually. And I think the Life Interferometer, if it ends up being funded, is going to be fantastic for that. Estimate the ubiquity of potentially habitable planets. So with that, I hope to have convinced you that there is at least some way in which stellar clustering modifies the properties of the planet population. And to wrap up, I would briefly like to bring everything back together. So this is the Emazex simulation that I showed earlier in the talk, where we basically see the formation of a Milky Way-like galaxy over cosmic history, with all of the individual clusters forming in that system. And if you look at what we call the cluster formation efficiency, so the fraction of star formation occurring in bound clusters in this galaxy, as a function of redshift, what you see here is that that is a steeply increasing function with redshift, right? So at high redshift, the gas pressures were higher, more stars formed in clusters. Now, what that means is if you look at the fraction of stars born in clusters here at the top, many planetary systems must have been affected by their environment. Whereas at the bottom, when few stars are born in clusters, few planetary systems are affected by their environment. So that means that towards higher redshift, more planets will have been affected by their environment. But there is something really striking about this figure. Do you see those peaks? These are galaxy mergers. During those galaxy mergers, the gas density and pressure are increased, a larger fraction of stars is being born in clusters, and therefore a larger fraction of planetary systems is being affected by their environment. These are megaparsec scale events that end up affecting the AU scale properties of planetary systems. This is the magnitude of the problem. It's crazy, and it's amazing. So if you look at the solar system, or yeah, the solar neighborhood, I should say, this is the star formation history. You see that starburst here? The idea is, in this paper by Ruiz Lara and collaborators, is that this was triggered by the passage of the Sagittarius dwarf galaxy. The sun formed here. Right, so that galaxy, that merger right there. The sun formed there. So if the solar system did not form in relative isolation, like we see there, then the nearby population of protoplanetary disks may tell us a lot less of our own origins than we might have thought. Might not be representative at all. So to wrap up, I've talked about how stellar clustering connects the formation and evolution of galaxies to the formation and evolution of us. I've talked about how stellar clustering drives the baryon cycle in galaxies, disrupts giant molecular clouds by early feedback, and we can use that as a subgrid model to accurately model stellar clustering and galaxy evolution across cosmic history. I've talked about how we can then use simulations of the entire stellar cluster population to enable the use of globular clusters to reconstruct the assembly history of the Milky Way. Those events eventually might have affected our own existence. I've shown how stellar clustering shortens protoplanetary disk lifetimes at high gas densities and pressures, mainly by external photoevaporation, but also dynamical interactions. And then finally, I've shown how stellar clustering shapes the planet population in terms of the architectures of planetary systems, but also in terms of the properties of the planets themselves. So our existence may be one of the biggest multi-scale astrophysics problems. And the challenge of trying to understand this complete ecosystem might seem challenging at first. But I hope to have convinced you that this is becoming a tractable problem. We can start connecting all of those different scales and mechanisms. So when faced with this challenge, we shouldn't look scared, but cool. Thank you very much for listening.
Thank you very much for this wonderful talk. I really enjoyed it. Thank you, Diederik, for this one. And now the talk is open for questions. So I think Rainer will manage the questions over there. Okay, Rainer?
No.
Can you see the questions and the raised hand here at Zoom?
Let's see whether we can see the questions.
Well, none yet.
We can, yeah.
So, yeah, first of all, thank you very much, Diederik. This has been a wild ride. I hate long talks, but I did not record for a single moment. So, fantastic, and yeah, really, you compressed a year-long lecture into an hour, so I forgive you. And now we would like to have the floor open for questions. You were first, Adrian.
Thank you so much for your nice talk. And I would like to address a question related to something if for me it's very also very interesting. Mm-hmm. So the mass of the planets is related to the overdensity. Mm-hmm. Let's say the mass of the stellar structure somehow. So which is the physical mechanism that you can invoke in order to explain this? The angular momentum conservation, because you are considering that when you have the higher stellar masses, then perhaps the system is going to be more stable when you consider the formation of more massive planets. Or
so I'll just repeat the question for online. So the question is, there is this relation here between being in an overdensity of the field and the eventual properties of the planets. You're mentioning mass as an example. Is there what is the physical mechanism that could be responsible for that? Yeah. So I think there is actually a relatively weak dependence of the planetary mass on the phase space clustering. I think that is actually one of the weak, if not absent, dependencies. We find the dependence is strongest in terms of indeed orbital architecture of the planetary system, and then also indeed planet radii, so atmospheric properties. The masses of the planets are not that dependent. But having said that, I do think it is a very relevant question to ask, okay, what is the physical mechanism that's responsible for all this, right? And of course, given that these things are not, these overdensities are not representing the stellar clustering at birth, it has to be something that happens over longer timescales, and the only reasonable mechanism you could then think of is a form of dynamical perturbation. So if there then is a form of dynamical perturbation, you need to think about, okay, there is some form of passing field stars or something like that. Turns out, if for the galactic disk you calculate the encounter rate with passing field stars, given the semi-major axes of the planetary systems, that encounter rate is much too low. So yeah, you will get encounters, you will get flybys at, you know, maybe a few tenths of a parsec, but that's not going to do anything to those compact planetary systems that we see here, right? I mean, this is like up to 10 AU is what we're plotting here. It's also because, of course, larger radii planets are harder to detect. But that is a problem. So therefore, the only way of getting your angular momentum transport inwards into the centers of these planetary systems that we see here, you need some intermediate step. You need to have some form of companion potentially, or you need to have some form of binarity or multiplicity potentially. And I personally think that that is where the solution is actually going to come from. I think that in the end, we're going to need to take a very serious look at binaries, and especially wide binaries or soft binaries, to figure out how these could act as an intermediary to transfer the angular momentum from sort of close encounters to the eventual central planetary system. But it cannot be direct, because then the encounter rate would be too low. Yes. Yeah. Indeed, we are looking at simulations to try and address this question, actually, now. So indeed, that is the way forward. So I realize it's not exactly the answer to your question, but I hope it answers your question nonetheless. Okay, cool. Thank you.
Thank you for the talk. I just have told me that I stopped at the Galactic scale because as soon as you can resolve a star, for me it's like overwhelming. But I was wondering, you summarize that galaxy evolution actually plays a major role in this scenario, even for the planet formation evolution. So then, what about AGN phase activity in galaxies? How does this affect, for instance, stellar clustering evolution, and then how this whole picture of AGN activity can be, let's say, or has imprints in this whole picture?
So the question is, how does AGN activity affect the entire picture that I sketched in my entire talk? Do you have another hour? So I mean, what AGN activity is going to do is going to change the baryon cycle in your galaxy, and is going to change the outflow rate into the IGM, and of course, you know, mostly for the massive galaxies. In Emazex, so all the stuff we did on the globular clusters, that actually includes an AGN feedback model. So, you know, it's the Eagle AGN feedback model. It's, I think, by far no longer state of the art, but there is a model. In the stuff I showed earlier, where we changed the feedback model based on observations, that did not include AGN feedback because we wanted to isolate exactly what the stellar feedback did. In terms of the planetary system properties, I think that what AGN feedback would do is it would, of course, directly only affect the interstellar medium close to the galactic center. However, the fact that you've got maybe more precipitation from the circumgalactic medium could end up changing the ISM properties in the outer galactic disk. How would that affect the planets? That's a really good question. You would need to just, yeah, you would need to look at simulations for that to see, okay, I mean, you switch it on and off and you look, okay, how do the properties of my galaxy change? But what we see in the end here for the planets is that what is important is a small velocity dispersion, right? Because the phase space clustering is mostly in velocity space. So if there is any way in which nuclear activity can affect the stellar velocity dispersion at a distance of 10 kiloparsecs, one way or another, and undoubtedly really indirectly, then that would have an impact here on the planets. But it would be through many epicycles.
If I may interject, I think for a system like the Milky Way, for example,
sure.
can neglect
yeah.
historically. Yeah, it's irrelevant.
But
yeah.
The question was also if you could see imprints from that activity.
Mm.
I mean, I don't know if it is. Well, let's say that, for instance, that our own galaxy went through an AGN phase at some point of its life. So would you see those imprints, for instance, in this overdensity that we said?
Yeah, right.
Not only from satellite galaxies and interactions between galaxies, but also from the AGN.
Right. Could there be ripples in phase space driven by past AGN activity? In theory, possibly, but I think that would be drowned out by other dynamical effects. So satellite galaxy passages, spiral arm perturbations are going to have a much stronger impact in an absolute sense. And therefore, if there is an impact, I think it would be undetectable.
Thanks so much for such a beautiful talk. I've loved it. I work in extragalactic science, but I've loved how you connect with us. So that's great. And so my question is related to extragalactic, of course. Mm-hmm. You've shown simulations of galaxies. So the question is, do you include any bulge component in your simulations, or are just pure disks?
So the question is, to what extent do we model bulges in our galaxy simulations? In the cosmological ones, I mean, we absolutely do include bulges. I mean, they form cosmologically. So we have galaxies. The beginning. Yes. Yes. So in the, sorry, people on Zoom, that I'm now very big, but I'm just going to the right slide. Here, this one. Yeah. So this one is a good question. I actually don't remember. Melanie, do you remember? No. Yeah, we should have had the first author here. So I think it has a bulge. It's not going to be dominant. The thing is, I mean, this is just the proof of concept of the model. We have now run a suite of cosmological zoom-in simulations of Milky Way mass galaxies. There we have bulges. And one of the key questions here is how this new feedback model actually affects the bulge growth in those cosmological zooms. I think that is a really interesting question because, you know, what you, oh yeah, wrong window. What you see here is just how the structure of those galaxies changes as a function of the feedback. So now imagine applying that at redshift 2 or redshift 1, and it's probably going to change how your bulge is forming. So I have no doubt you had a direction you wanted to go with your question, but I think this is the exciting direction, is bulge to disk ratios are definitely going to be affected by using observed feedback.
Exactly, because we know that galaxies with different bulge disk ratios behave not so equally. And
yes.
There are differences and impacts.
Yeah.
So it should be interesting to see how the presence of, the relative importance of the bulge have an impact in those simulations.
This is actually, indeed, this is one of the things we actually want to look at for the paper in which we're writing up the cosmological zooms. So stay tuned. We're going to do that. Thank you. Thank you.
Are there any questions online? I think we cannot see the chat here. René?
No question online, no.
Okay.
No question in YouTube. either.
If I may ask a question, I'm giving the word to myself. So I have a gazillion questions, but two of them that I still remember from the hour-long talk. So first one, when you have the probability density function of gas, and you say it's a function of, so it's either broader or narrower, which is a function of
gas pressure.
So do you actually see also in your simulation that at high gas pressures you have a different initial mass function than at low gas pressures? Because you mentioned the initial mass function.
Stellar initial mass function, no. Sorry, to repeat for online, the question is, okay, this changes as a function of the gas pressure, the width of this gas density PDF. Do you see an impact on the stellar initial mass function? We do not resolve the stellar initial mass function, so we're just assuming it.
Okay.
There is an impact on the star cluster initial mass function.
Okay,
so at higher gas pressures, basically more massive clusters can form. That doesn't mean your mass function shifts. It means that because the star cluster initial mass function is a parallel with index about -2, it just extends to higher masses. So there is always an exponential truncation at high mass. It just moves to a higher mass. And that is what you get at higher gas pressures. Yeah.
And I forgot completely, in all your checks on the planetary systems, did you also select for the mass of the host star?
Yes, yeah, yeah.
You did that. I think it's in the list probably.
Here.
Okay, yes.
So indeed,
yes.
Yeah. But that is mostly because we took a narrow stellar mass range. So then by construction, yeah, we control for that.
Any last questions? Online questions?
Nope, I don't think there are online questions. I'll be around for a day and a half more.
Yes.
So
to finish this,
maybe you should have the microphone. Yep.
So to finish, you've seen that Diederik and his group, they're really almost in anything. So I strongly encourage you to use this opportunity. Melanie will also give her talk tomorrow about the baryon cycle, and I think it's great opportunity to interact also with Melanie. We will tomorrow evening, we will try to go to dinner. So if anyone is interested in joining Diederik and Melanie for dinner, please drop us a message or walk by. So Melanie and Diederik currently are in John's office if you want to catch up with them. And yeah, please use the opportunity. They have to leave on Friday morning. And yeah, tomorrow Melanie is going to give her talk at 12:30. Don't forget about it, even though there's some rumor about Event Horizon Telescope tomorrow. They're telling us something. It's 3, so please. Okay, thank you very much. Thanks, Diederik.